Alright, let's start off, as I usually do with these test equipment videos, by referring to Chuck Penson's excellent book, Heathkit Test Equipment Products. I'm going to flip directly to the chapter on digital frequency counters and multimeters. By this time, I've covered almost everything in this chapter, except for the most recent frequency counters. But going back to the beginning, as far as frequency counters go, the IB-1101 was Heathkit's first frequency counter, and their first digital product, really. Although some of their more proficient or professional level devices had a little bit of digital in them before this, but it was pretty early on. And is a 15 megahertz frequency counter, came out in 1970, only lasted through 1972. And in order to make it useful, the IB-102 was produced just a year later, and that was a 175 megahertz frequency scaler. So you could use this with this in order to get it up to a reasonable range of frequencies that it could measure. You would take a higher frequency and either pass it through with a ×1 multiplier, or divide it down by 10, or divide it down by 100, and then that lower frequency would be applied to the IB-101. Of course, you would lose resolution when you did that, but at least you could get an idea what a frequency was up to 175 megahertz. In 1972, the same year that the IB-101 was discontinued, a couple of new frequency counters came out. The IB-1101 was a 100 megahertz frequency counter, looked just like the 101, except it went up to 100 megahertz. And this was made up through 1975. I have videos on all of these, by the way. At the same time, they realized that $295, essentially $300 in the early 70s, that was quite a chunk of change. So they came out with a reduced cost version of it called the IB-1100, and it was made for the same period of time. This was very comparable, except that it couldn't go up quite as high in frequency. It only went up to 30 megahertz, and it had a cheaper, it was still metal, it wasn't like it was made out of plastic or anything, but the switches weren't quite as nice. It used a larger Nixie-tube size, and actually looks very nice. It's a bit smaller with the case, is, you know, a bit smaller than the other models. It didn't have the nice bail handle, you know, a number of cost-cutting things. But it was still a very nice meter, and a little more consumer-friendly in terms of cost. Also in 1972, the IB-1102 came out. This was a 120 megahertz frequency counter. So not that different from its contemporary, the 1101. Not that much of a difference in frequency. But in addition to going up to a higher frequency, it also had more digits of resolution. Instead of only 5 digits for the 1101, it had 8 digits. And this was made up through 1977. 1 year after the 1102 came out, Heathkit produced their most glorious version of this series, and that's the 1103, which is the subject of this video. It went from not too bad, you know, you jump up from $374, $375 to $400, and you jump from 120 megahertz up to 180 megahertz. You know, quite a screamer for the time, unless you're going to, you know, high-end, very expensive professional equipment. But instead of just having the very simple power switch and kilohertz megahertz switch, you got a lot more control. There were 3 different gate times instead of just 2, and there was also a multiplier, so you could take lower frequencies and multiply them either, times 1, which in which case there's actually no multiplication going on, or times 10, or times 100, or times 1000. And a special circuit in here would take the lower input frequency and multiply it by one of those factors, enabling you to get a higher resolution version of it. If you had a counter like this and you're plugging in a fairly low frequency, or even this one with only 5 digits, you might only get the most significant couple of digits, and then everything else is kind of off to the right and not displayed. But with the multiplier on here, not only could you go up to 180 megahertz, in which case you don't need the multiplier, or you could bring in some lower range frequencies and multiply them up and get a much higher resolution with that 8-digit display. So pretty nice meter. So I'm going to focus on this 1103, and let's just see what Chuck has to say about it. The 180 megahertz IB-1103 was another push up the frequency scale, making the 1103 Heathkit's fastest counter to date. Heath did this with the addition of a built-in phase lock frequency multiplier. Features an 8.3 digit Nixie display, so I need to clarify that. The 1102 had an 8-digit Nixie display, 8 Nixie tubes. The 1103 also has 8 Nixie tubes, but not shown in this photo. It also has a 1 over here to the left, which is not illuminated in this picture. So you actually had double the number, because you could roll over all 8 digits and then get a 1 in the most significant position and then fill these up again. So it was able to read twice as large a number as the 1102. You had a push button select of times 1, times 10, times 100, and times 1000 multiplier. Frequency range 1 Hz to 180 megahertz. Gate times of 1 millisecond, 100 milliseconds, or 1 second. Sensitivity is 50 millivolts to 120 megahertz. In other words, from 1 Hertz up to 120 megahertz, the sensitivity is 50 millivolts. And above 120 megahertz, it's 100 millivolts. The input impedance is 1 mega ohm shunted by 35 picofarads. You had AC or DC coupling, which none of the other ones did. You had no control of the coupling. So that's another addition here, but it's not done with a switch. You actually have separate BNC inputs. The time base is, or the maximum input is diode protected, 120 volts RMS up to 20 megahertz, and then the input voltage, the maximum input voltage, drops rather precipitously down to 10 volts at 200 megahertz. So 120 volts at the lowest frequency is only 10 volts at the highest frequency. Time base is a 4 megahertz. Temperature control or temperature compensated crystal oscillator. And let's see, replaced by the new IM 4110, 4120, and 4130 series, which are the later models that have LED displays. It's this series here, which I don't have much interest in, and I don't plan to ever do videos on. I'm more interested in these older models. Anyway, so let's get into the rest of the video. Alright, here's the artifact. Just as I received it from eBay, I believe this was in some sort of a shop environment. It was sold by a transmission repair company. That doesn't mean that they don't also have a store that, is affiliated with them, that maybe they've got a thrift shop next door or something. I don't know, but it's possible that they might have had this thing in there as a piece of test equipment, using it in the repair of transmissions or something, and decided that it was outdated or something. I don't know. But it's got all the crud on there you'd expect from being used in a shop environment. They did not say at all whether it worked. It didn't even say power's on. It's just, there it is. A couple $100. It's a more sought after model. But unlike the others in the series, and this most closely resembles the IB-1102, the earlier models were not quite as tall, but otherwise they looked the same. But beginning with the IB-1102 and then this 1103, the case was a little taller, actually the same case as the IM-102 digital multimeter. So unlike any of those in the series, it has extra holes in the top and bottom case for getting rid of excess heat. They must have finally got to the point where they decided it was getting too toasty inside these. And the thing also weighs a metric ton. It's a very heavy piece of equipment. It's like, really hard to pick up with one hand. It's just like a block of lead. Without having my IB-1102 right in front of me, I think it's really the same case. The oscillator adjustment, the oscillator switch, the external input, the line cord socket, the heat sink with the extra 2 voltage regulators on it. I think that's identical to the IB-1102. And I think there's going to be other similarities as well. Let's take off the top. I've already loosened the side screws. So this guy has the same circuit board in it as I had already deduced from studying the front counter circuit board for the IB-1102, that it had extra pads and positions for things on it which were not being used. And I suspected that that was because the same board was probably utilized in the 1103 with its extra capabilities. And also you can tell that this circuit board is just covered with a big thick layer of dust, which you would expect if it was in a shop environment instead of a lab environment or a home environment. It's just dirty. It has the same 8 Nixie tubes, but it also has that one neon bulb there. I think it's the only one in the series, not counting again the IM-102, which has its 3.5 digit display using a neon bulb as a 1 in the most significant position. But I also recall from the schematic of this circuit board on the IB-1102 that it had an extra couple of flip-flops on it which were not being used in that particular counter. And I suspect that again they were probably doing something extra, such as this, adding the capability of a 1. And indeed there is no overrange indicator on this one, as far as I can tell. If it is, it's burned out probably, because I did do a very preliminary test. There are 3 lamps on this one on the left side. The 1102 I think only had 2 of them, and then 3 over here where there was only 2 on the other one. And this one has or 3 different frequency ranges, so it needs 3 bulbs. And I believe that the bottom one over there is gate, and one of them would be overload or over range. And this one also has an unlock bulb. So I'm not sure if all of those are working. Like I said, I did do a very preliminary check. I just plugged it in real quick hooked it up to a signal generator and ran it through. It seemed, I think, pretty much all of the possibilities of the buttons, and seemed like I was getting sensible readouts, although the Nixie-tubes were all at weird angles and things. So I did a little bit of preliminary straightening up of those. I also found that the thing had apparently been dropped at some point, and the power transformer was kind of an odd angle in its rectangular chamber. And when I checked it from the bottom, I could see that the chassis was malformed. So I think it probably got set down very hard at some point, or dropped even. And I was able to straighten it up pretty much. Selective tapping with a wooden dowel and a hammer on the bottom, and also putting a rod with a drilled out end over that screw, which was leaning inwards a bit, and prying it back to vertical. The 1103 here also has a third circuit board. This space was empty on the IB-1102. This would be the input circuit board here. Offhand, I'm not sure that it's the same one that was used in my IB-1102. If you watched that video, you may recall that I'd determined there were at least 3 different versions of this input circuit board. Just from a quick glance, I think it might be the same version, but again, I'm not positive. The time-based circuit board probably is the same one. And then this is the multiplier board here, which handles the extra functionality here where you can shift in different multipliers. I think it's giving you more different gate periods, and maybe some other things as well. The power supply board may be a different version. I had assumed it would be the same, but I don't remember there being a large TO220 type of semiconductor on the board for the IB-1102. So this may be, even though in general looks similar, there might be some differences in that regard. I don't know why this board is sitting at a weird angle. It would suggest that the connectors on the bottom are not square for some reason. Don't know about that yet. Anyway, like I said, I think it's basically working. I did notice a couple of extra decimal points that were turned on, and a quick check of the schematic shows that those are driven strictly by switches, not by electronics. So it could even be some elements in the Nixie-tube shorted out. I'll have to do some investigation on that. The strips here are very close to the bottom of the case. They were on the 1102 as well, although I'm not sure. No, I think it had to be the same basic chassis design. But that one didn't have this big insulator, and this one does, to protect against those being shorted to the case bottom. So again, this is very similar to the IB-1102. There's a few more wires on there because of the extra stuff. And this circuit board has been added. That's what all the switches are connected to. And also all of the decimal points from the Nixie-tubes come out on all these wires here, and they're all going directly to this board. And from the schematic it shows there's a lot of logic being done by the switches to figure out in various combinations of the buttons when various decimal points should be showing. There's also an additional input on this that none of the other ones in the series had, and they're just marked AC and DC. The other ones had just a simple or single input, and there would be a series capacitor to drop out any DC component of an AC signal. Here the shielded cable going to the input is connected to the DC, the DC BNC jack, and then I think the series capacitor is dropping out the DC component right up here, which suggests it's not being done on the input circuit board. And honestly, I don't remember. It's possible that the cap might have been in this general position anyway, but mounted differently. I just don't have a good enough recollection of the IB-1102. Anyway, so this is just my preliminary. What do we have? Okay, I'm going to replace these electrolytics. The only 3 electrolytics on the entire IB-1103. There's a number of tantalums on some of the analog boards, especially I think the input circuit board. But as far as aluminum electrolytics, these are the only ones in the entire thing. And it's exactly the same board as the board that was on the IB-1102 that I restored. So I'm just using the same Illinois capacitor. That's Cornell Dubilier or whatever they call themselves. I'm using a 22 microfarad 25 volt in place of the 2000 microfarad 15 volts that was in the original. And I'm using a 100 microfarad 100 volt in place of the 100 microfarad 70 volt. And they're smaller than the originals, which just barely fit in there and actually lean a little bit to the left, or the sides. Okay, those capacitors have been replaced. Alright, I've rolled on a coat of the specially tinted enamel that I had made to closely approximate the Heathkit dark beige from the New Look series. Gonna put another coat on, but I ran out of rollers, so I gotta go to the store. Okay, after the second coat of paint, my sump pump chooses this moment to turn on. Alright, I've been wrestling with a gnarly problem on this IB-1103. Everything seems to be working except some of the decimal points are misbehaving. They don't turn on correctly at the right times or combinations of settings. And it's not a digital logic issue with any of the ICs. Indeed, everything that takes place with shifting the time-based circuit board from one mode to another, switching the frequency multiplier board from one mode to another, supplying power to various circuits in various combinations of modes, and of course setting where the decimal point happens for each permutation of gate, time, and multiplier selection. And that's all done with these actual switches. So on one side they all solder onto the switch circuit board, and then there's also a fair amount of wiring and some components on the component side of the board. And the Heathkit schematic made it kind of hard to follow, so I mapped out the circuit the way that Heathkit had it drawn, or at least with the connections that Heathkit had, but reorganized because they were just scattered all over, and it was, you know, things weren't grouped properly. They had inconsistencies in how they depicted the switches and their orientation, so I reoriented everything on a sketch that had all the switches that were deciding the frequency multiplier mode, all the switches that decided the time base mode, and the switch that determines whether or not the multiplexer board itself gets power, and also an input to the input circuit board is controlled off of this one switch. And then there's a whole bunch of switches in a big array here that together determine whether or not the hertz lamp, the kilohertz lamp, or the megahertz lamp, which of those turns on. And then the rest of these are determining which decimal point turns on out of 5 possibilities. This is the display with the most significant 1 only position, and then the 8 positions of Nixie-tubes. While they all the Nixie-tubes have decimal points, only those on what Heathkit calls V1, V2, V3, V4, and V5, only those decimal points are used, and thus those decimal points are at the lower right-hand corner of those tubes, or to the lower right-hand corner of the characters portrayed by those tubes. So it didn't make any sense to me as I tried to map my way through it. There was a lot of irregularities and things not turning out correctly, multiple lamps being on at the same time, and this is again just studying the switch logic. Multiple lamps being on at the same time when only one should be, places where there should be grounds but it's not shown, and vice versa, a missing connection between a couple of switches, all sorts of stuff. So I went back and traced every stinking wire and redrew the switch circuit board with blue and red traces for foil side and component side respectively, and then wires that go off into a wire bundle are depicted in one color coming off the board, and wires that go off differently without a wire bundle, in other words directly to the counter circuit board, are depicted in a different color, and also the wires going to the 3 light bulbs for hertz, kilohertz, and megahertz. All of these ultimately function by providing a ground path. So, well, I should qualify that. Almost all of them work by providing a ground path. These switches here, for switching gears of 2 of the smaller circuit boards, the time base and the frequency multiplier, those aren't just ground. There's also a plus 5 volts. So the switches decide whether a particular signal is going to be at 0 volts or ground, or at plus 5 volts, a logic 0 or a logic 1. And likewise, these 3 switches that are controlling what the gate time of the time-based circuit board is going to be, those have 2 signals which can be 0 or 1. So those do have 5 volt potentials being switched through them, as does this one here, because it's providing plus 5 volt logic power to the multiplier or frequency multiplier board, and the input to the time-based board. Also, 5 volts is used to power these 3 bulbs, but here the 5 volts is not being presented to the switches. Rather, it's the other side of the bulbs that go through the switches trying to find a path to ground, and only one should be allowed to find a path to ground. So that's what's going on there, but the bulk of these switches are all just trying to find a path to ground for one and only one of the 5 decimal points. So whichever one has a path to ground, that decimal point will light up. And So I went through all the permutations, of which there are 12, and traced everything out where signals went and dead ended, where signals made their way through. And I just did that all 12 times. And then I translated the results to a spreadsheet. My diagram number, the time-based setting, the multiplier setting, which range lamp should be illuminated, which decimal point should be on, and then those other control signals and the switched 5-volt power. Their statuses are on this adjacent and aligned chart. And what I found out was, in most of the modes, or most of the permutations, at least one decimal point is on which should not be. For example, when you're in the 1 millisecond time base and the ×1 multiplier, it should be only the V4 decimal point that's on, but in reality, in spite of what the switch logic says it should be, you also get the decimal point on V3. When you're in 1 millisecond and the ×10 multiplier, you also get the 3 decimal point on in addition to the 5 that should be on. When you're in 1 millisecond and ×100, only the correct decimal points lit. In the ×1000, you once again get the 3 lit. And then when you're up in the 100 millisecond ranges, you may get the 4 turning on erroneously. You may get the 4 turning on erroneously again down here. And when you're in 100 milliseconds and ×1000, you get the 4 and also the decimal point on V1. And it goes on like that. I studied very carefully all the switches and wiring and did not find any short circuits, abraded insulation, or anything like that. And it occurred to me that there's this metal frame for all the switches. That's what holds them together in their assembly. And it sits down on top of the circuit board really close. And in my sketch here, this area here, which has primarily foils on one side of the board, but it also has a couple foils on the component side of the board, and those are exposed to being shorted out by the metal frame. Well, I checked the Heathkit manual. I couldn't actually see anything in there. It just looked like it was metal on top of the circuit board. But I did find in the Heathkit manual assembly instructions that there's a very thin piece of fish paper that is sandwiched in there between the metal frame and the circuit board, and that should be an insulator. But I went down and found places where connections should not be made, but yet there is continuity with a continuity tester between the frame and various points in the circuitry wherever we have foils that are going out to the front of the board. So it does appear that there is some shorting going on, presumably a breakdown in the fish paper. Don't really know exactly where the short is. I thought about dismantling this whole thing and trying to correct it, but I decided that since everything else is working, the chances of really breaking something and mucking things up, rendering this whole thing inoperative, those chances were pretty high. And I wouldn't be able to get any replacement parts, so I've reluctantly decided to accept this scenario here where I'm just going to know that there's some malfunctioning of the decimal points. And I think what I'll do is I'll make a little chart and affix it to the back of the meter or something that says, hey, when you're in this combination, you're going to get this extra decimal point turning on, and here's the one that should be turning on, and ignore the incorrect ones. Again, not that this is ever going to get used again for real, but I think I'll do something along those lines. Meanwhile, I also have to reassemble this and fix a couple of broken wires. Heathkit loved using solid wire for hookup wire applications, as they would say. They rarely used stranded wire unless it was on a shielded cable or something. And that's all well and good when you build something the first time, but then when you're trying to troubleshoot something and you're flexing things around, the wires start snapping off. And that has happened in at least a couple of places that I know about, and might very well happen again, thereby screwing up even more stuff. It could get very sticky very quickly. And here's the input circuit board. This is very close to being the same circuit as the input circuit board on the IB-1102. The main difference between this board and that board is that this has a few extra parts on it. I believe there's an extra IC, probably this one right in the middle of the picture. And that's because depending on what mode you're in, range and frequency multiplier mode, the input signal may need to be routed off of this board to go through the multiplier and then back to this board and pick up from there with the counters, the first stage counter. So it's primarily just the provision for that signal leaving and coming back in with the electronic switching of the signal, either the unfrequency multiplied or the frequency multiplied version, that necessitates this being a slightly different version of the board. And here's a rear of the input circuit board. Here's the time base with its temperature compensated crystal oscillator on the upper right. And here's the rear of that circuit board. Here's the frequency multiplier board with the shield around the phase lock loop circuit, removed temporarily just to see what's inside. And here's the rear of the frequency multiplier circuit board. Here are the three shielded chambers for the three plug-in circuit boards: the input circuit board, the time-based circuit board, and the frequency multiplier circuit board. If it wasn't for the fact that this third bay, the top one in this image, has connectors in it, this would look pretty much exactly like an IB-1102. There's a few giveaways. There's a few extra components on the counter circuit board down there and up here, transistors. But otherwise it's very nearly identical in appearance. And here's the same view with the three circuit boards plugged in. And here's the bottom view of the chassis. Counter circuit board in the back there, switch circuit board here in the front, the connectors for the input circuit board, time-based circuit board, and frequency multiplier circuit board, and the power supply circuit board, and of course all the wiring running between them, including the ferrite beads and so on that are scattered around in here. So let's just do a quick walkthrough. I'm going to some degree treat this video as an addendum to my IB-1102 video, because for the most part they're the same. There's a lot of circuit board commonality, and except for the user interface being more elaborate, there's really more alike than different between them. So I don't want to go over everything in as great a detail as I did with the 1102. If you have more interest in that, you can watch that video. So we start off, we have all of the Nixie tubes on the front, and there's actually a light shield behind them, and that prevents any ambient light from the outside from going through the window, lighting up components in the circuit board or reflecting off the aluminum here, and then coming back out, and the viewer seeing all of that, and it kind of junks up the quality of the display. So by having that behind the Nixie tubes, you just see the Nixie tubes. This is the counter circuit board here, and for the most part you just have a bunch of decade counter ICs. These are all TTL, and then a bunch of 4-bit latch ICs, and then a bunch of BCD to Nixie-tube driver ICs, one per Nixie-tube. So 1, 2, 3, 4, 5, 6, 7, 8 for all the Nixie tubes. There are also a couple of more ICs here. These are flip-flops, and these are associated with that extra neon bulb, which you can see in there, which fills in the most significant digit, which can either be nothing or it can be a 1, which is what you get when the neon bulb is lit up, so it looks like a 1 from the front. That's more commonly seen on digital multimeters to fill in the most significant digit. And this is the only Heathkit Nixie-tube based frequency counter that uses anything besides Nixie tubes for the display. It has that extra most significant digit, and that is handled by these ICs here and the driver transistors. There is also a bunch of little tiny incandescent bulbs here. They're very small, like a fat grain of rice. There's 3 of them on each side. They're not neons. The lower end frequency counters do use neon bulbs, but the 1102 and the 1103 here both use the little incandescent bulbs. They give a little nicer look, so it's a little more professional. Tiny little wires on them. They're only running at 6 volts. They're designed for 6 volts, and they're actually powered from the 5-volt logic power supplies. So they're running a little bit soft of their normal rated voltage. The bulbs are either controlled by logic, in which case a transistor will short one side of a lamp to ground and the other side's tied to plus 5 volts to get the light bulb to turn on, or it's done through combinations of switches on the input push button switches. So it depends on which bulbs we're talking about, how they're controlled, whether it's just by switch logic or by solid state logic. And here's the back side of that circuit board. Now this small circuit board here is the switch circuit board, and it takes all of these push button switches on the front and combines them in various ways. Down here is the input coupling capacitor. This is the AC input, so AC coupled input. The signal has to go through this capacitor to get to the cable that goes into the rest of the circuit. But if you plug in the input to the DC one here, then the entire signal is passed down the cable to the input circuit board. So normally you would use the DC one and just have the signal go through unmolested, but if you have a signal with a considerable DC offset or DC component and you want to strip that out, then you would connect your input to this so that the signal has to go through the capacitor, which would remove any DC component of the signal and leave only the AC component. So that's what that's doing. And when I first started restoring this, I thought, well, this capacitor isn't in the right place. You can't remove the bezel with it. Here it should be between the chassis and the bezel, because it seemed like the sketches in the manual said it should be there. So I removed the bezel and I rewired it to there, but then I found that there was no way to put the bezel back on without crushing or shorting one of the capacitor wires to the chassis. You just couldn't make the tortuous path without shorting out to the BNC jack's body or actually to the chassis directly, either which is circuit ground. So I had to remove it and then put it back the way it was here. And then on further inspection of the diagram, I realized this is the way it was intended to go all along. The other thing we have here is the backs of all of the circuit boards, the plug-in circuit boards. This is the power supply circuit board goes here. The multiplier circuit board here. The time-based circuit board here. And the input circuit board here. So there's just hard wiring connecting all this stuff together. And then the wires from the secondary, the power transformer, come over here. So these are the outputs of the power supply board, and then the various control signals and signal paths going every which way around here, and then various programming signals and so on going back and forth, and the signals going to the counter board. So it's all done here on the back with hard wiring. Going around the top, we've already looked at the input circuit board. We have the power transformer here, and the two, I believe they're 1 amp 5-volt regulator ICs. And by the way, this is a very heavy piece of kit here. And when I received this, it had been dropped, and it had stove in the back panel. It was bowed way in, because these had hit the floor probably, and I had to straighten that out as much as I could. Kind of difficult with the heat sink on it, and the cans have been crushed a little bit, but not enough to damage their internal circuitry. So you got the big heavy power transformer here, fuse way down there, wiring for the regulators here, and then your various diode bridges made out of discrete diodes, filter capacitors, and this is for the power supply that generates the high voltage for the Nixie tubes. It only has a single diode and this capacitor, and those two together off the high voltage winding of the transformer produces the necessary high voltage to make the Nixie tubes work. And then one of the bridges in this capacitor, these together here, make up the power supply for the analog circuitry, and then components over here on the left side of the board, a couple of transistors, a couple of Zener diodes. Those split that in half to create a plus and minus power supply for the analog. And then these larger diodes in this diode bridge and these two larger electrolytics in parallel form the unregulated side of the 5-volt logic supply, and then it goes from there to the voltage regulators to produce two different 5-volt supplies, one from each of these. And it's just split up. One alone can't handle everything. These old TTL chips especially draw a lot of power and get a lot of heat in them, and they run pretty hot. Although not as terrible as the ECL chips that are over here on the front. And now I can't remember if these are ECL or RTL. I'll have to clarify that when I edit the video. Anyway, it's a different class of logic ICs that can go a lot faster. So this is the input circuit board. all of the transistors and things down in this section take care of converting the incoming analog signal, which comes through this shielded cable here from the input jacks. And the board can be unplugged, and then the shielded cable can be unplugged from the board like that. And then you've got the circuit laid out here, front and rear. So again, all the analog front end stuff is pretty much over in this part of the board. A number of transistors there. And then we get into the ICs. And the 4 flip-flops that are in here form the front, or the least significant decade counter. So for the least significant digit of the display is handled right here on this board, but it's built out of flip-flops instead of a discrete decade counter. And then because the voltage levels, the logic levels in this type of circuit are not compatible with TTL, you've got all these transistors here which level shift the outputs of this first decade counter down to TTL voltage levels so that they can go into the remainder of the circuit. And there is one lone op amp here, which is part of the input conditioning circuit, which I'll talk about. So this is the time-based circuit board. This is what generates the clocks that control and synchronize all the other aspects of the frequency counter circuit, and that includes the gate signal, which is what admits the input signal after it's been conditioned by the input circuit board, passes it on to all the counters on this board, again except for the least significant digit, which is handled by the flip-flops on here instead of by decade counters on this board. The actual oscillator is this temperature compensated, that's what the TC is for, and then the XO means crystal oscillator. Temperature compensated crystal oscillator. It produces a 4 megahertz signal at a pretty good accuracy, and then it's all just TTL logic on here. So all these ICs on the top, there's 6 of them. Each of those is a decade counter, and even though they're arranged in this wonky way, they're really all just in series. They just had to be arranged this way to fit on the board. And then the other things here are either flip-flops or discrete logic ICs, and there's also a multiplexer IC on there, which is controlled by some of the aforementioned signals from the switch circuit board logic, with telling this board which time base mode it should be in, the 1 millisecond, the 100 millisecond, or the 1 second modes. And that's handled by the multiplexer chip picking off different points in these counters, and then they've been divided down by different amounts because of that. And that gives you the different clock signals. And in sync with the clock signals are the transfer and reset signals, which control all these ICs here. And here is the multiplier board. It's all, again, TTL logic. And underneath this shielded box, or this shield box, is an additional IC, which is sort of partially analog, partially digital. It's a phase lock loop IC. And I'll talk more about that when I go through the circuit theory. But it's very sensitive, so it has to be inside the shield here. It's really just one IC and several support components under that can. But again, the function of this board, and it includes some more decade counters, by the way. The goal of this is to take a low frequency signal and multiply it up to a higher frequency signal so that it can be displayed with more resolution by the counter circuit board. And if you don't need to do that, then the switches on the front panel, you just put it in ×1 mode, and then the signal is bypassed around this board so it doesn't even go through it, and the board itself is powered down entirely when not needed. Okay, here's just a little demo. There's a loose connection somewhere in there. I haven't been able to find it so far, and I often lose the gate signal. But at the moment it's working, and I'm giving it a 1 kilohertz input with the time base set to 1 second and the multiplier set to ×1. In other words, the multiplier is not doing anything. I am displaying that the reading is in hertz. Ignore the decimal points, and I'm getting essentially 1 there, and the gate indicator is flashing. If I go up to 2, it rolls up to 2, 7, 25. Oh, I lost the gate again. Picky thing. Whoop, there we go. We got it again. 25. So that's with the multiplier set to ×1. If I set the multiplier to ×10, now we're still reading in hertz, but we're reading way up here. We have more resolution. It's still about 25. This is where the decimal point should be. Well, it's still in hertz, so the decimal point still shouldn't be there. It's just reading this many hertz. No, I'm sorry, it should have a decimal point here, shouldn't it? Yeah. So this decimal point's correct, these are not. And anyway, the multiplier is working because the signal's being multiplied up to that point. If I go to the ×100, it stays in hertz because it has a big display with lots of digits. So now it's reading 25 up here, and the decimal point should be here. It went away from here, but it did not appear up here, as it should. I'm sorry, I'm still putting my foot in it. It's still reading in hertz, not kilohertz, so there shouldn't be any decimal points there. Takes a little bit to get used to this meter. And if I put it up at 1,000, it gives me an unlock. It's really out of range, so I have to put it back to this, but I can change to 1 millisecond, and now I'm in kilohertz, and it's putting in the proper decimal point, 25 point whatever, and I can change the multiplier. I can go to ×10, and now it's only in megahertz. So again, the decimal point's in the wrong place. I can go to ×1, and it's reading the 25 way down here. If I go to 100 milliseconds, I get the 25 up here. Because now it's in kilohertz, this is the correct decimal point, this one is incorrect. And if I go to ×10, it's in kilohertz, and there should be a decimal point here. But notice the resolution changes. That's due to the multiplier. ×100. Now it's still in kilohertz. Decimal point should be here, not these two places. We've added more resolution. If I go to 1,000, I'm going to get an unlock here because it's out of range. It's still giving me, now it's not really multiplying properly because it's out of the range of the circuit. So, you know, while it's working at the moment, that is essentially what's going on. We, again, have 3 time bases, 1 millisecond, 100 milliseconds, and 1 second. The gate indicator shows us the gate, although on the higher speeds, it just shuts off. But at 100 milliseconds, it flashes like that. At 1 second, you can see it flashing at a 1 second rate. And depending on the combination of the time base and the multiplier, we'll get different readout or indicators here for which units this is in. However, with the false decimal points, that'll throw you off as to the reading if you don't already know approximately what it should be. The reason for these problems, as far as I can tell, I don't think it's an intermittency in any of the circuit boards. It appears to be an intermittency in the programming switches. In other words, these switches. And not the switches themselves, but the wiring. The programming signals which control the time-based circuit board, the programming signals are coming from this. They're iffy, and it cuts out depending on the orientation. If you don't have this thing set just right, it must be just a hair contact that can either be open or closed, and you can tip the thing a few degrees and it works or not. It's very frustrating and unreliable. But basically all the circuitry is working. It's this electromechanical corruption that seems to be the root of all the problems. I've thought about several things I could do to make this better. One would be to try to find comparable switches that are on the same spacing and would work with these same buttons, and make a whole new circuit board and wire it up, and problem would go away. But I collect these things to be in original condition as much as I can, and wholesale replacement of this with a new board is something I don't really want to do. I can just put a note on this saying that it's working, but it has an intermittent issue depending on, you know, when you pick it up and set it down again, you might have to jack around with it a little bit to get it working again in terms of the gate signal. And I definitely have other ones in my collection which are working perfectly except for some little intermittency that I have not been able to track down or resolve. So I just put a little note on them saying, you know, this is working, but, you know, due to age and so on, it's been deemed not practical to try to get that issue to go away. I may still decide to address this again at some point in the future. I have 2 more of these, and they all have exactly the same problem. The decimal points are shorted out on the circuit board, although this is the only one that has the intermittency with the gate signal. And I've thought about pulling this circuit board out and putting one from another one in there, and that may still happen, but I didn't want to delay making this video to the point when I might decide to do that, and it might be successful down the road. I just wanted to get the documentary finished and just explain the aberration there, but basically it's good, except for that. Okay, there's the beauty shot. Okay, here's the massive schematic for the IB-1103, and because almost all of it is identical or nearly identical to the IB-1102, which I've already done a video on and dissected the circuit or the schematic and the circuit theory, I'm going to skip a lot of it here, and if anybody wants to see more in-depth coverage of the parts I'm going through quickly here, you can watch the IB-1102 video. So once again, any frequency counter is going to have a power supply, it's going to have a time base which generates the gate and some other signals, but primarily the gate signal. And it's going to have some sort of a front-end circuit that conditions the signal being tested, because it can have a wide range of waveforms and voltages and offsets and all sorts of things, and impedances, voltages. So the front-end circuit conditions whatever the input is to a uniform logic level that the rest of the circuit can use. Then there will be a big counter chain, a bunch of decade counters, and the time base will reset all of those and then open the logical gate, allowing the input signal, after it's been conditioned, to go into the counters. And the gate is open, if you will, for a very precisely generated amount of time, typically 1 second or 1 millisecond. And so the input signal is only allowed to get through to the counters during that precise window of time. And then at the end of that gate, when the window closes, then the counter can't accumulate count anymore. And there is a brief period of time when the contents of the counters is then moved into a memory device, a latch or whatever, that can hold it, and then the counters are reset, the gate is opened again, another reading is taken, and this all repeats. And during the time when the reading is being taken, the previous count that's stored in the memory is used to display the value. So it updates the display once every time the gate occurs. So that's the essence of the frequency counter. So I'm going to start with the power supply. This is really identical to the power supply in the IB-1103. You've got your transformer on the front end, power transformer. You've got 3 windings. One of them uses a Villard doubler circuit, which is a series capacitor, and then a diode from there back to the other side of the winding, and that rectifies and doubles the voltage, and that achieves, in this case, a pulsating DC voltage that's 100 volts or somewhere above it, and that's needed to operate the Nixie tubes in the display. Very simple circuit. Then we have the logic power supply. This uses a full wave bridge, 4 diodes, a couple of filter capacitors in parallel, and then 2 integrated circuit voltage regulators. One of them handles the time-based circuit board and the counter circuit board, and the other one handles the input circuit board, the logic portion of that, and the switch circuit board. Then we have the remaining winding, which gets, again, full wave bridge rectified and filtered. And then we have a current limiter made out of a couple of transistors, and that feeds into a pair of Zener diodes. They're drawn funny here, but they really just go from this point to this point, and therefore they develop a fixed voltage across them, but the point in between the 2 Zeners is tied to circuit ground. So essentially it's taken the regulated Zener voltage and split it in half, with the upper half being called the plus 16 volt power source and the other side being called the minus 16 volt power source. So that is used for the analog front end circuitry. Let's take a look at the input circuit board, and this is really 2 circuits on one board. The left half, pretty much everything from here to the left, is the part that conditions the input signal coming from the input jacks. and the right half of which is the first decade counter in the counter chain that accumulates the count during the gate period. The rest of the counter chain is on the counter circuit board, but the first decade's worth is on this circuit board. And part of the reason for that is that you want it to be close to the input circuit physically for interference reasons, and also because there isn't enough room on the counter board, and thirdly because the counter circuit board is all TTL logic, whereas the logic circuitry on the input circuit board is ECL logic, emitter coupled logic. And that's done because the input frequencies here can be quite high, and normal TTL of the period when this was developed couldn't keep up with those frequencies. So the first decade's worth of counting is done with ECL, which can handle the higher frequencies. And then once it's been divided down by 10, which is what the decade counter does, then the frequency is starting to get into the range where the TTL logic on the counter board can handle it. So there's that. So again, I'm just giving the quick overview here. We've got the two input jacks, one for AC only signals and one for DC, which means it can't really be DC exactly, or there wouldn't be a signal. It's not like it's a power supply, a fixed voltage. But DC here means any signal that you want to put into it, really, including an AC component, a DC component, whatever, and then the input circuitry will deal with it. But if you have a input signal that has a lot of DC component to it, and you might want to strip that out before it gets sent into the input circuit, then you can use the AC jack. So really, if you've got anything with a large DC component or DC offset, it's probably better to use the AC jack. And a capacitor here is what strips out the DC component if you come in the AC jack. Then you go through a short shielded cable to the input circuit board. There's a FET front end that gives it the high input impedance. And then we go into this differential amplifier circuit, which again I explained in some detail on the IB-1102, so I won't go over that here, but it's a differential amplifier, and you end up with the input signal and a complement to the input signal, and it's been amplified and buffered and everything else, and then it gets fed into this IC, which is a Schmidt trigger. It's really a flip-flop, but it's being used in a clever way that makes it function as a Schmidt trigger, where it's being set with this signal and reset with the complementary signal. And because we don't know about offset and things in this circuit, the signal coming out of one half of the differential amp could have quite a different voltage than the signal coming out of the inverse signal, if that makes any sense. The voltage could be different on the inverse signal. And to deal with that, both of those signals, in addition to going to the inputs to the Schmidt trigger, they also go down to an op amp that's set up to take the average of the two signals. So the average of a voltage on a non-inverted signal versus the voltage on the inverted signal. And from that you get a correction voltage. It's a DC voltage, and that's fed back into this transistor, which then affects one of the inputs to the differential amp in a way that it can correct for the offset. So if you have too much of a difference in voltages between those, then this detects it and corrects for it by feeding back into the differential amplifier. It's all part of making sure the input signal, whatever it is, gets conditioned properly. And now we're into ECL territory with this first IC. Now in the IB-1102, the output of that Schmidt trigger goes directly into a set of 4 flip-flops, which are connected together in a way to comprise a decade counter. So a divide by 10 counter. But also configured so that it has a BCD output from the 4 flip-flops, and that's needed by the downstream circuitry. And again, this is all ECL logic, but because we have a frequency multiplier function on this counter, we can't go directly from here to here. If we're in the times 1 multiplier mode, then the logic here gets steered by one gang of the switch when it's in the times 1 position. So because the Schmidt trigger is made out of a flip-flop, you actually have the Q and the Q naught outputs. They're exactly the same, but they're complements of each other. When one's high, the other's low, and vice versa. So if we're going straight through here in the times 1 mode, then we use this output, and it goes through the logic gate and then on to the flip-flops of the first decade counter. But if we're not in the times 1 mode, then this gate is turned off, so the signal can't go directly through. Instead, its complement is taken out here, leaves the circuit board, and goes into the frequency multiplier circuit board. All the junk gets done to that, and then it comes out, having been frequency multiplied, and it comes back in here and goes to this other gate that's just like this one, except this one allows the signal through when you're not in the times 1 mode, where this one let the signal through when you are in the times 1 mode. And then once again it continues on to the first decade counter. Because the decade counter is working at ECL voltage levels, and everything downstream is TTL and has different voltage levels, there's a set of 8 transistors here, 2 for each bit of the BCD count, and those convert the ECL levels per bit into TTL levels. And then they come out and they go into the counter circuit board. These are the 4 signals right here. 1, 2, 3, 4. Those together comprise the BCD signal from this first decade counter. Now, here's the thing that's different from, it's really an identical circuit board as far as the etched pattern on the board as the counter board used on the IB-1102. But if you remember that video, there's a number of places where there's odd jumpers on the board and unpopulated places for ICs to go. So that's what I'm going to primarily address here. So here you have 1, 2, 3, 4, 5, 6, 7, 8 decade counters in a chain. Notice that for the first decade, there is no counter. There are counters for the other 7, but not for the first one, and that's because that counter is what was over here as already discussed. So it's feeding its BCD data in here, and it goes into the first latch. This is the least significant latch of the display. And then all the other 7 decade counters all have their own latches, and you have a total of 8 latches, each driving through a display driver IC, driving the Nixie tubes, all 8 of them. So what's going on down here, and why were there these weird jumpers over in this area of the board on the IB-1102? Well, that's because even though the input frequency has been divided down by 10 on the input board, at the highest input frequencies this counter is designed for, you can still have frequencies coming out here which are a little faster than these TTL decade counters are designed to handle. But only by 1 bit after that signal has been divided and it's this one particular signal here. That's the one that'll be changing the fastest. This is still a little too fast to go right into the next decade counter, which would be the first TTL decade counter in the chain. And I should backtrack a little bit to refresh your memory, if you've seen the other video, that all these decade counters are really just 4 flip-flops in a single IC package. Very similar to the circuit used here for the first decade counter, done with discrete flip-flop ICs. But in here you've got 4 flip-flops in an IC already connected internally to act like a decade counter with BCD outputs. But they're set up really so it's a single flip-flop, which is a divide by 2, followed by 3 more flip-flops set up as a divide by 5. The 2 of those together making the divide by 10 or decade counter. So we've exceeded the capabilities in terms of frequency of the very first flip-flop in this first decade counter IC. So how to deal with that? Well, we export that as a separate IC, which is just a flip-flop, and let it be used in place of the first flip-flop in this IC, after which then we use the remaining flip-flops in this IC, and then going downstream the frequencies progressively lower and lower as it keeps getting divided down, so then we can use all 4 flip-flops in all subsequent ICs. So this is just a flip-flop set up as a divide by 2, and this particular IC has a higher frequency rating than these decade counters. So that's why it's being done that way. But on the IB-1102, this IC was not populated on this counter circuit board. Nothing was in that position. And indeed, the first decade counter here, all 4 flip-flops inside are utilized. So there are jumpers on the board, because it's again the same board, to select how the signals get routed around here, whether they have to go, whether this signal has to go through this flip-flop before going to here, or whether it goes directly into this IC and utilizes its internal first stage flip-flop. So that's what was going on there. At the tail end, I already mentioned that in addition to the 8 digits of Nixie-tube display, so 8 full-digit resolution, and that's identical to the IB-1102, the IB-1103 we're talking about here also has that extra 1 in the most significant display position. So there's an extra flip-flop at the end. After the signal's been divided all the way down and you're getting up to the most significant digit, its overflow gets sent down to, this is actually the last counter, its overflow, instead of just going to the over indicator, meaning that you've overflowed the counter chain, it goes into this extra flip-flop, which captures that 1 extra position higher than the most significant full digit. And then that goes into a holding flip-flop, which is just like one of the 4 latches in any of these memory chips, and then goes through a driver transistor and operates the 1 lamp in the most significant position. Then finally, if that overflows, then it goes to another flip-flop here, which records the overflow. It gets held in this 1 flip-flop that's a memory location for the overflow. That goes through the driver transistor, which operates the overrange indicator lamp. So all of these positions are here on the IB-1102, but they're interconnected slightly differently, so you don't have that 1 in the middle. It's sort of like a do-nothing logic, and then you've got this. So same circuit board, some extra components installed on the IB-1103 to give you that extra position out here and that extra bit of high frequency finagling on the other end. The other difference regarding the counter board, and I've already talked about this earlier in the video, that there's this switch circuit board, which none of the other frequency counters in this series have, and that's because they only have simple toggle switches for a kilohertz or a megahertz mode, for example, or a hertz and kilohertz mode. On the IB-1102, it's kilohertz and megahertz. So you only really have to deal with changing a decimal point once, and that can be done with a very simple switch. Here we have 5 different decimal points, which have to be moved around to different positions on the display depending on which time-based selection you've made and which frequency multiplier selection you've made. So there's some switches here which handle whether you should have the hertz, the megahertz, or the kilohertz lights on. Some combination of switches here. Well, I keep getting interrupted by phone calls, so I lost my train of thought, but I'm going to try to pick up from where I was. So there's additional switches from that cluster. 3 of them are used in a sort of a binary pattern for the 1 millisecond, 100 millisecond, and 1 second modes of operation of the time base, and that's related to the gate. It boils down to a pair of binary signals going into a multiplexer on the time-based circuit board. Similarly, there are 3 more switches. These are related to the times 10, times 100, and times 1000 multiplier functionality. And once again, it boils down to a pair of binary weighted digital signals, which similarly control a multiplexer and are part of the functionality of that board. So when I get into the theory of operation of that, I won't have to repeat the information about those switches. The final thing about these switches up here is a big cluster of them are used to figure out which decimal point should be illuminated out of the 5 decimal points that are used, depending on which time base and which multiplier mode are currently selected. So it does some switch logic in here, and it ends up influencing 1, 2, 3, 4, 5 decimal points on the 5 least significant Nixie tubes. And it's a simple grounding matter because the segments on the Nixie tubes are all energized on the anode side, and then the cathodes are dragged down to ground through the driver ICs, and whichever one is grounded is the one that has a current path and therefore will illuminate, and the decimal point is no different. So the decimal point needs, the cathode for that needs to have a path to ground, and that comes back up here and goes through one or more switches in the switch logic, and then finally makes its way back to ground, thereby illuminating one of the decimal points. And that's the fault of this particular meter I have, or this counter, and the other couple ones I have just like it. They all have the same problem, and that's that somewhere in this switch logic, because I think of the fact that some of the foils on the circuit board are underneath the metal bracket for the switches and circuit board, and that the insulator has failed in there, so that everything's shorted together, and that results in some erroneous illumination of the decimal points because it's finding unwanted or inappropriate current paths to ground. And that's not fixable without replacing the whole assembly, which of course would be very difficult, if not totally impractical, to do. On the time base, again, I covered this in considerable detail on my video on the IB-1102, and really the only difference between that and this one, and it's the same exact circuit board, is that on the IB-1102 there's only one programming pin coming to operate the multiplexer, and it's either on or it's off, and that gives you 2 choices, and it'll pick off the appropriate signal from the counter chain here. It's not the same as this counter chain, but the time basis counter chain, and that allows you to pick off for the kilohertz or megahertz time base functionality on that lesser frequency counter. But on this one, we've got the 3 choices of time base. Again, 1 millisecond, 100 milliseconds, and 1 second. So there have to be 3 choices. And even on the 1102, it being the same board, all the signals are being generated, but they weren't all being used because the multiplexer was only being commanded to choose 2 of them. Here we're commanding it to choose from 3 different possibilities. So that's really the only difference. It's all how these 2 inputs are driven from external circuitry, and otherwise everything on this board is identical to the IB-1102. Alright, so now the last part of the circuit I'm going to talk about is the multiplier circuit board. And because this is the one I'm going to be describing in some length, it being new to this particular frequency counter, I'm going to go to a sketch, which I think makes it a little easier to follow what's going on. Alright, here's my redrawn sketch. So the purpose of this circuit is to take lower frequency input signals and boost their frequency before being routed to the counter circuitry. And that is in order to get more resolution on lower frequency signals. For example, if you're only going to measure a signal that's, you know, say 1 kilohertz or below somewhere, even on the lowest time base range, you might only have a couple of digits of display, with everything else in the display being just a bunch of zeros. And you'd really like to have more accuracy, or more resolution rather. Maybe you'd like to see, instead of just 10 hertz, 1 0, you'd like to see 10.00 or something. Well, you can do that on this frequency counter by selecting the appropriate range and multiplier. But how do you get a low frequency signal that's coming in from the front jacks and turn it into a higher frequency signal so that it can be measured by the counter in such a way as to give you that higher resolution you need? You can't tell the counter to count differently than it does, but you can multiply the input frequency and multiply it exactly, and then add decimal points to show where you're going from the units to the decimal fractions. So that's what this circuit board does. And again, it has 4 modes: times 1, times 10, times 100, times 1000. In the times 1 mode, this circuit board is de-energized. It doesn't even have power going to it. And the conditioned input signal is just routed right around the multiplier and goes straight into the first decade counter of the counter chain. But if you're in the times 10, times 100, or times 1000 modes, then this circuit is energized and comes into play with the input signal being routed through it on its way to the counter chain. So here's a little sketch of the input circuit board, the digital portion of it. It has the Schmitt trigger, which I already touched briefly on, and that ends up generating an ECL level logic signal that is just a bunch of pulses that correspond to the input signal. And that is normally used by digital logic that's also on the input circuit board. So we come out of the Schmitt trigger, we go down here, and there's a electronic switch. It's done with logic gates, and it has 4 choices again: times 1, times 100, or times 10, times 100, times 1000. If it's in the times 1 range, the electronic switch, which is just a logic gate, takes that signal, goes straight around, and goes into the least significant digit of the decade counter chain, which is implemented in ECL logic on this same circuit board. But if you're in the times 10, times 100, times 1000 modes, then this direct signal is blocked. It can't get through this electronic switch, and the signal for the decade counter has to come through a different path, and that is coming from the output of the multiplier circuit board. So that same signal that comes out of the Schmitt trigger, again it's an ECL level logic signal, leaves the circuit board and goes into the multiplier. So the multiplier functions by taking the input signal and then not using it directly. There is a voltage controlled oscillator in the circuit, so it's given a voltage, and based on the amplitude of that voltage it generates a lower or a higher frequency digital signal, and then that signal is wrapped around and compared with the original signal coming in that you're measuring. So the copy is the one that's actually used by all the counter logic, and the original is just used as a basis to compare that to make sure that the copy is exactly what it should be. So how does the actual multiplication take place? Well, we take the newly generated frequency that comes out of the VCO, or the voltage controlled oscillator. We take that and we subject it to division. So we divide it by 10, and this is just done with regular TTL decade counters. And then we divide it by 10, then we divide it by 10 again. And the divided by 10 signal goes into a multiplexer, the divided by 100 goes into a multiplexer, and the divided by 1000 goes into a multiplexer. And then, as previously described, if we're in the times 10, times 100, or times 1000 range, the switches send the programming signals down here to the multiplexer, telling it which of those three divided frequencies should be then passed on to the comparison circuit that will compare it with the original signal. So think about this for a moment. Let's say we have a 1 kilohertz signal coming in, and let's also assume that the copy that's been generated by the VCO is 10 kilohertz, just for instance. So that 10 kilohertz signal comes in and it's divided by 10, which makes it 1 kilohertz. It's divided by 10 again, which makes it 100 hertz. It's divided by 10 again, which makes it 10 hertz. But because we've got the switches selected to look at the divide by 10, we're going to take only the divided by 10 signal, which is 10 kilohertz divided by 10, so it's 1 kilohertz. You have the 1 kilohertz signal gets passed through, and it's compared to the input signal. And if the input signal is 1 kilohertz, then it's considered locked, where the divided down copy of the signal coming from the VCO exactly matches the signal being measured in the terms of frequency. Then the multiplier is considered locked and no changes are made, but the signal that's sent to the counter circuitry is that 10 kilohertz signal. So it's measuring a divided or a multiplied by 10 frequency compared to the actual input frequency. So that's how it would divide by 10. If we picked off the divided by 100, now that's compared to the 1 kilohertz, and for that to be compared and locked, the VCO would have to be generating a 100 kilohertz signal, and so on for dividing by 1000. So you're always generating a signal that's new, dividing it by some factor of 10, and then comparing that divided down version by the original signal and seeing if they're the same. And if they're not, you adjust the VCO until you do get signals that are exactly the same. Therefore, your divided signal is exactly the same as the divided signal, or the divided version of the original would be if it was the input that was divided, but it's actually the copy that's divided. So I don't know if I made that clear or clear as mud. But let's go through the basic functionality. So we come out of the input circuit board, which is ECL logic. So we have an ECL level signal, and we apply it to an ECL amplifier here, which goes through this transistor and this transistor, that converts it from the ECL signal to a TTL level signal. So now we're in the world of TTL. All the other, well, almost all the other circuitry on the board is TTL rather than ECL. And then we have a very special IC called a phased lock loop. And what that's good for is comparing two different logic signals that are running at some frequency, you know, a square wave or something. And it compares both the frequency of the two signals and their phase. And it will output information based on if they're in phase or not, and it will output information based on if the frequencies match. There are these two outputs that are used in this particular circuit, and let's say that frequency A, that's the signal coming in here from what you're actually measuring, if that's higher than frequency B, which is the signal fed back through the decade counters from the VCO. So let's say that the input signal is a higher frequency than the divided down VCO frequency, which means that the VCO is not operating at a high enough frequency and it needs to be adjusted. So in that situation, there's always pulses coming out of these two pins, and they are running at the frequency that we're talking about, I believe. It doesn't really matter for this discussion, though. There will be some up and down waveform activity, perhaps like this coming out of pin 13, and pin 2 will have something similar, but the amount of time the signals are high versus low will be different between the two of them. So if A is higher than B in terms of frequency, then the pulses coming out of 13 will be low more often than they're high. But if it's the other way around, where the frequency A is lower than frequency B, then the pulses will be the other way around in terms of which one is low more often than it is high. Well, how do we use that information? Well, first off, we run through a couple of logic buffers. They don't do anything to the signal except invert it. And then those are applied to a couple of NPN transistors. There's a capacitor here. It's a tantalum electrolytic capacitor with a series resistor. And the goal is to charge or discharge this capacitor to have a different voltage on it. So charged to a different voltage. If this transistor is turned on, it tries to short out or discharge the capacitor through this resistor back to ground, which would decrease its charge and gradually lower it to a lower and lower voltage. On the other hand, if this transistor turns on, it in turn turns on this constant current source, which tries to charge the capacitor through this resistor. So there's always some charging and some discharging going on, because both of these pins are on sometimes and off sometimes, assuming the two frequencies are not identical. One of them will always be pulsing on more often than the other one's pulsing on. And so one of these two transistors is going to win. One of is charging the cap at a certain rate, and the other one's discharging the cap at a certain rate. And whichever one is on more often than the other one will prevail in terms of causing the voltage on the cap to rise or lower. So this is how we convert the output of the phase lock loop to a voltage. And then we have a voltage controlled oscillator, and that voltage control is the voltage on this capacitor. So the voltage on the cap reflects the adjustment that needs to be made to the VCO frequency in order for it to match the input frequency. Then we go through a buffer. It's just an FET, so it's a source follower, and it doesn't put any drain on this capacitor because it's such a high impedance. So the capacitor doesn't even know that this FET is here, but it's making a copy of that capacitor voltage out here. Now that's applied to another FET, and this FET has a Zener diode from the positive power supply through it to this capacitor, and this is another form of constant current source. So depending how high the voltage is coming from over here, the rate of change will be more or less on this capacitor, and you'll end up with a ramp signal. So it'll start out at a lower voltage and then ramp to a higher voltage, and that voltage is sampled through another FET source follower, so it doesn't load the capacitor, it just makes a copy of the capacitor's voltage, and that's applied to a couple of differential amplifiers which are configured as a Schmitt trigger. And the other input to the Schmitt trigger is a voltage reference circuit. It provides a constant, reliable, tightly controlled voltage. So this is basically looking for when does this ramp reach the voltage of this voltage reference. The ramp will be taking more or less time to reach that voltage depending on what the voltage on this capacitor is. So the ramp will be ramping up to the same voltage all the time, but it'll be taking more or less time to do so. Whenever the ramp does reach the reference voltage, then the Schmitt trigger sends a signal out here, which is essentially the output of the VCO. But to get it oscillatory as it needs to be, it also goes through these two transistors and then reaches back around here and shorts out this capacitor. So once again, we're charging up at a rate that's based on the VCO control capacitor's charge, and when it reaches the threshold of this voltage reference, it reaches around here, turns this transistor on, which shorts out this capacitor, so the voltage on it drops back down. Immediately, that causes the Schmitt trigger to no longer see a voltage matching the reference, so its output turns off, and that turns this transistor off, so it's no longer shorting out this capacitor, and it's once again allowed to ramp up based on the current coming from here. So you get a sawtooth waveform, and the period from one resetting to the next one is the frequency of the VCO. So you can get quite a wide range of voltages coming out, or frequencies coming out of the VCO, depending on what the voltage is on this cap, which in turn depends upon whether or not the generated waveform from the VCO is higher or lower in frequency than the incoming signal from the input to the frequency counter. So that's how we get a copy frequency. Now, how do we adjust it to make sure it's the right frequency? Well, first off, the pulse coming out of here is very short. It's just whatever time it takes to notice that it's reached the threshold, flip the Schmitt trigger, turn on the transistor, and discharge the cap. And then that pulse will go away, so you actually have a very short pulse blip, you know, that comes out every so often, very short pulse. In order to condition that pulse, That's this signal here. It's run into the input to a flip-flop. This is again an ECL flip-flop, and that essentially acts like a divide by 2. So it's taking whatever frequency is here and divides it by 2, and in the course of doing that, it turns it into a square wave instead of a brief pulse waveform. Then the output of that is converted back to TTL again through a transistor. And by the way, it's ECL because of the high frequencies that could be found in here. The frequency of oscillation can be 1,000 times the input frequency. Although that doesn't work if you're putting in a really high frequency to the counter. It only works when you're dealing with lower input frequencies, which of course is why there's a multiplier circuit here in the first place. It's applicable to the lower input frequencies, not the higher input frequencies. So it still can be high enough that it needs to be conditioned with ECL instead of TTL, and that's why there's an ECL flip-flop here instead of a TTL flip-flop. But then all the logic that's following it is TTL, so that transistor turns the ECL voltage levels back to TTL, and now we go into a decade counter. But as I pointed out elsewhere, these decade counters are really a divide by 2 flip-flop followed by 3 more flip-flops configured as a divide by 5, and the 2 of them together make a divide by 10. And so here we're not using the front flip-flop, so all we have is the divide by 5 part. Why is that? Because we are preceding it with a divide by 2 flip-flop here. So this plus this makes a divide by 10. And that gives us our divide by 10 signal for the multiplexer. And then by further division, a divide by 100, and further division, a divide by 1000. And that TTL signal wraps around again and goes to the phase lock loop. So that is how that works. Now, what happens when we finally adjust the VCO to precisely match, after it's been divided, precisely match the input frequency? When the phase lock loop detects that the 2 frequencies are exactly the same, instead of pulsing the outputs on these 2 pins, it just locks them high. They just go to logic 1 or logic high instead of oscillating on and off like I had in my little sketch here. Well, that turns these transistors off. So highs here get inverted to lows, lows into the NPN transistors turns them off. So we're neither discharging nor charging this capacitor anymore. And because we're monitoring the charge on the capacitor through this FET with its very high input impedance, this cap just sits here with whatever voltage it had on it last, but it's no longer being manipulated up or down. It's just being measured, and it'll stay that way for quite a long period of time because of the action of the FET. That's like a sample and hold type of arrangement. It doesn't have to hold it indefinitely. It just needs to hold it long enough that it doesn't sag before it's next needed again, which is happening pretty fast actually. And this is a tantalum capacitor, so it has minimal internal leakage. So all of that together makes for it holding a stable voltage for as long as we would need it to do so. So we're in this mode again where both outputs here are high, and this is an AND gate, and it detects when both outputs are high, and when they are, the output here turns logic low. So it's saying that when this is logic low out here, or logic 0, that means the phase lock loop is locked, which means that the generated frequency is exactly the same as the measured frequency, although we're only measuring the divided generated frequency, not the raw generated frequency. That's important to keep in mind. So if it's unlocked, in other words, where it's searching, trying to get the VCO to match the input, which it may or may not be able to do depending on the frequency range of the input. If it is locked, this is low, and that turns off this NPN transistor, which means there's no path for current to flow through the unlock lamp on the front panel. Therefore, it does not indicate unlock, and that's appropriate because it's locked. Now, if it's not locked, then this gate will never show you an output that is pulsing. It'll always be either just 1 or 0. And so if it's unlocked, you get a 1 out here that turns on the transistor, providing a path to ground from the 5 volts through the unlock lamp to ground, thereby illuminating an unlocked condition to the user. At the same time, this signal is inverted by a logic gate and applied to another NPN transistor, which the output is taken off the collector, and that's fed around to this NOR gate. Well, the NOR gate here acts like a switch in this configuration. So whenever we are locked, this transistor here is turning this point to a logic 0. And this being an OR gate, it can pass through the signal on the other input as long as the remaining input is logic 0. But if this turns to logic 1, then the output just goes fixed, and it will no longer pass the other signal through. So this is the VCO's output, and it'll pass through as long as this is locked, and then that goes out of here. Again, this is an ECL logic gate, so the output is ECL logic levels. So this is the VCO signal running at ECL logic levels. We go back around, we re-enter the input circuit board, and because we're in the times 10, times 100, or times 1000 ranges, that signal's just passed through the electronic switch and goes down to the first or the least significant digit of the decade counter. And from there, it's just like normal operation. So I hope with this fairly long description, I've made it clear how this thing works. Alright, just a quick walk through the manual. IB-1103 Frequency Counter. Somebody's penciled in various things that have gone wrong with this. IC124 defective, swapped ICs, the other one worked, part number, one of the bulbs won't light, an IC pin broken off. Presumably all that stuff was fixed because I didn't have those issues. Before I get into the rest of it, this is the only manual I have that still has the greeting from the assigned silent partner, in this case a certain George Keane, technical consultant. Hello, I've been assigned as your personal technical consultant during the assembly and checkout of your kit. Since we're partners on the project, I'd like to introduce myself. I'll be a silent partner unless you need me, but want you to know I'll be most happy to help you in any way possible if you do have any technical questions or problems with your kit. And then also saying you can also go to your local Heathkit Electronics Center if there is one. So, 2-page table of contents. Introduction. The Heathkit model IB-1103 Frequency Counter is an accurate, compact, lightweight, and rugged 180 MHz digital frequency counter. The following features make this counter an ideal test instrument: the 8.5-digit readout with associated overrange and range lamps, high accuracy, a sensitive high impedance input circuit, and a unique digital frequency multiplier. A readout of 8 cold cathode display tubes, those would be Nixie tubes, and a 1 indicator lamp provides 9 positions to display frequencies. Also, 6 other lamps provide range, gate, overrange, and unlocked information. High accuracy is achieved by digital techniques and a 4 MHz temperature-compensated crystal-controlled oscillator. A high-impedance FET input circuit presents minimum loading to the circuit under test, while the automatic level triggering feature provides simple hands-off operation. The unique wide-range digital frequency multiplier multiplies input signals by 10, 100, or 1000. Thus, an input frequency up to 10 kHz can be measured to 0.001 Hz. So that's a boost of resolution. Other features include plug-in integrated circuits, plug-in circuit boards, detachable line cord and test cable, a 3D-tent position bail handle to position the counter at desired viewing angle, and an optional 110 to 130 or 220 to 260 volt transformer wiring. Since this is a pretty complicated kit, there are different chapters in it, each one addressing a different subsection of the kit. So general unpacking notes, assembly notes, but nothing specific. Started with the easiest circuit board, the power supply board. Parts list, parts pictorial. This manual is not being cooperative. Parts list and pictorial continued. Step-by-step instructions. And I think I'm actually going to rebind this manual because it's quite a thick manual. The pages don't want to lay flat, and a lot of the pages are falling out, which just makes it awkward. So I think I'm going to stop recording and do some binding on this and then resume. Okay, presto changeo, now I have a wire binding. And I'll get back to where we were. Step-by-step assembly. It's pretty simple, so it only takes 2 pages. Then we get into the time-based circuit board. There's a fold-out with the parts pictorial. The number of parts is remarkably small. It only takes 1 page. Start out with the assembly right away. Several pages of assembly for that board. Then the input circuit board. 1 page of parts list. Parts pictorial starts out. Parts list continues on the next, the other side of the page, and the pictorial continues. That's an unusual way of doing it. I don't recall seeing them do it quite that way before. Step-by-step assembly. I'm compromised here because I don't have a flat backdrop for this, so it's actually bending the binding a little bit, making the page turns harder than they would be normally. This is a more complicated board, so it takes more pages. Then the frequency multiplier circuit board. It's going to do the same thing as the previous one, having the parts list and parts pictorial spread over a couple of sheets. Then the counter circuit board, same thing. The parts pictorial is actually on the opposite page. And it seems like there should be a larger parts list, but in reality, the nature of this board is it's just a few parts, but over and over and over again, so makes sense. Then the extender circuit board, which I don't have. And then the chassis. Parts list is much longer. And it includes the switch circuit board. Here's that now infamous piece of very thin fish paper that gets put along the edge, and it seems to break down over time. Heathkit likes to use fish paper for an insulator. I mean, that's one of the reasons why it exists, but normally you put it on something that isn't intended to come in contact with electrical stuff, just in case the electrical stuff comes close to it. But this case, I think they misused it by deliberately putting it as a barrier between 2 metallic things that are in very close proximity and would be touching if it wasn't for the fact that the fish paper is jammed in between them. I don't think that's appropriate use of the paper, and I think it bit them in the butt a little bit here. There's a big fold out and it folds out again. Lots of diagrams on this one. Wiring harness. This one is feels like a fold out, but it isn't. Lots of detailed drawings on this one. A lot of parts being mounted on the chassis. Another big fold out. And then it folds out that way as well. So lots of pages in fold out. Mounting the power transformer. More fish paper. It's kind of funny. They had very detailed drawings here for how big to make the small piece of fish paper and where exactly to stick it, and showed it several different ways. And on mine, it's supposed to be on the right side of this metal plate, and the person who built it put it on the left side where it does no good. This is there to, in case the circuit board, the input circuit board that goes in this chamber, actually, if it happens to get pushed that way, the back side of the RCA phono jack that's on the circuit board could come in contact with the chassis, and that's what the fish paper is there for, and that's an appropriate use of fish paper. Here's assembly of the light shield. Mounting the light shield to the chassis. Another fold out. How to install the Nixie tubes. How to wire up the 6 small incandescent bulbs. How to mount all sorts of things on the chassis and wire things up. Inserting the circuit boards, putting on the Heathkit label, making up the test lead. Here's another fold out. This is the one that shows how to connect the test lead back to the clock circuit in such a way that you can use it for self-testing. And more on making the test lead. Initial tests. Final assembly, putting on the side rails of the chassis. Mounting the handle. Big piece of fish paper. Big piece of fish paper on the bottom of the chassis half shell, just in case it gets pushed inwards and might come in contact with the bottoms of all the chassis connectors, but not normally in contact with it. Again, proper use of fish paper. Putting on the feet, assembling the chassis half shells. Calibration, there isn't much to it. Diagram of all the things on the front panel. Operation and application. And they do make a good point here right away. They clarify that the display updates at different rates depending on which time base you're in. And if you're in the 1 second time base mode, you have to wait 3 seconds after connecting a signal that you want to measure before the display is guaranteed to be accurate. And that just has to do with the updates and the asynchronous nature of the signal being measured and the clock signal in the frequency counter. And also the inherent plus or minus 1 count that will be present at all times, and a little diagram explaining why that is so. And I don't think there's a frequency counter made that's any better than plus and minus 1 count for the same exact reason. talking about how to use the frequency multiplier and stressing that it's really for increasing the counter resolution and also a way to get a quick display of low frequencies. Operating recommendations, making sure you don't connect it to certain types of power which are ground referenced and could blow up parts of this device. How to do certain high frequency measurements with just a small coil of wire connected to the test lead. Then we're into the in case of difficulty section, which is a bit larger because of it being a fairly complicated product. And they've got this here, it's almost in the form of a flow chart. Sometimes they'll use a table, sometimes they use a flow chart. This one, they do it in a flow chart kind of arrangement. Specifications, more specifications, fold out with a block diagram, and a third page of specifications. Circuit description, general theory of operation, input circuit board description, counter circuit board, time-based circuit board, use of the external oscillator, frequency multiplier circuit board, and then finally the power supply. Chassis photographs, top and bottom, circuit board X-ray views. The only board on this one which is single-sided is the power supply board, so they don't actually need an X-ray view. Time-based circuit board, front and rear, input circuit board the same way. Frequency multiplier board, counter board, same way. And this one's better than the IB-1102 manual I have. By and large, the alignment of the red and the gray is better on this one, but it's not even consistent on this one. For example, that's pretty bad registration right there between the red and the gray. It makes it very hard to follow these things when they're offset that much. That's a failure of whoever Heathkit had printing these things. With equipment even available in the 70s, having such bad registration was borderline unforgivable. Switch circuit board and then voltage views. A switch supplement diagram. They obviously felt the need to have a more concise pictorial schematic of just the switch circuit board. I don't think it's as good as the one I drew, but it's way better than trying to figure it out from the general schematic. So at least they have that. Identification chart. Nixie-tube and transistors. Heathkit's part numbers, or possible generic part numbers. More transistors, diodes. The integrated circuits. I think there's about 3 pages of these. There's 4 pages. And then there's the schematic in its small form. This is still a big schematic. This is the one I've already touched on in the circuit theory section. There is a bigger version of this which is a fold out and separate and not bound into the manual. It's a little easier to read. Oh, yeah, so that's the last page. Then we're into the customer service and the back of the manual.